GameSci.com. GameSci.com.
Yippee-ki-yay! Time to learn some sum of products. Let's start with a truth table. Here's a truth table with two inputs, A, B, and an output of F. Sum of products is going to let us generate a Boolean algebra expression that represents that truth table. From the sum of products expression, we could then create a circuit that represents that sum of products expression. Truth tables and Boolean algebras and circuits are all about design and analysis of digital logic. That's what sum of products is going to allow us to do. Design and analyze digital circuits. First and foremost, focus like a laser on the lines of the truth table that output 1. I've boxed those two in right there. Sum of products has everything to do with these lines and nothing to do with the lines that end with 0. Sum of products says look at the lines that output 1. Let's build some Boolean terms for those lines. Look closely at the first line with an output of 1. A is 1, B is 0. The Boolean term for that input, read out loud, is A and not B. On a computer keyboard, you might type it like this or this. Looking closely at the second line with an output of 1. A is 1, B is 1. That outputs a 1. The Boolean term for that input, read out loud, A and B. On a computer keyboard, you might type it this way. Or the terms together. Sum/or the terms together to form a sum of products expression. Here is the final sum of products expression for this truth table. Read out loud, it is A and not B, or A and B. Circuit diagram. This is a circuit described by the sum of products expression. This circuit implements the truth table above it. How could you prove that? For every possible input AB, does it have the exact same output F? For every input of AB, does this circuit produce the same output? Let's do it. For each line of the truth table, let's see if this circuit and this Boolean algebra expression produces the same result. When A is 0 and B is 0, F is 0. Plug the values into the sum of products and it certainly produces a 0. Plug the same values into the circuit and it produces a 0. Remember, not B is 1 when B is equal to 0. So A is 0, not B is 1, A is 0, B is 0. That produces a 0 on this AND gate and a 0 on this AND gate. Fed into an OR, the output is 0. Looking at the sum of products expression, 0 and 1 for this AND gate produces a 0. Or the two zeros on this AND gate produces a 0. The sum of products produces a 0. The truth table says output is 0. The sum of products expression says output is 0. And the circuit diagram outputs a 0. For this line of the truth table, it certainly agrees. Testing row 1 of the truth table. When A is 0 and B is 1, then F should output 0. Plug these values into the sum of products and it certainly is 0. A is 0, not B is 0. Remember, not B is 0 when B is 1. Or 0, 1 for A, B on the input. Well, that's a 0 if you AND them together. That's a 0 when you AND them together. ORing them together outputs a 0. Plug these same values into the circuit diagram and it is also producing a 0. Two zeros on this input produces a 0. A 0, 1 on this AND gate produces a 0. Two zeros fed into an OR gate produces a 0. Remember, not B is 0 when B is 1. B is 1 here, so not B is a 0. Testing row 2. When A is 1 and B is 0, A is 1 and B is 0, F outputs a 1. Plug these values into the sum of products and it certainly is 1. 1 and 1 on this AND gate produces a 1. With a 1 on this side of the OR statement, the output of the function has to be a 1. This sum of products expression certainly produces a 1 for these two inputs. Plug the same values into the circuit and it also produces a 1. Two ones on this AND gate produces a 1. A 1 fed into this OR gate guarantees a 1. Notice how the sum of products is true when the truth table for the same input is true. And this must be the circuit because it also produces a 1. Testing row 3. When A is 1 and B is 1, the output F is 1. When A is 1, B is 1, the output of the truth table is 1. Plug these values into the sum of products and it certainly produces a 1. If A and B are both 1, this expression produces a 1. If you have a 1 on either side of the OR statement, the output of the sum of products has to be a 1. Plug the same values into the circuit diagram and it produces a 1. A 1 and a 0 on this AND gate produces a 0. But a 1 and a 1 on this AND gate produces a 1. This 1 fed into an OR gate outputs a 1. We have proven the sum of products expression and the diagram correctly implement the above truth table. All the inputs produce the exact same outputs. Boolean algebra. This all ties into Boolean algebra. Sum of products can be the starting point for Boolean simplification. Our expression is A and not B, or A and B. If you apply this Boolean algebra law, A times B or C in parentheses equals A and B in parentheses, or A and C in parentheses. You can simplify it to this expression, A and in parentheses, not B or B. Well, that's an identity. Not B or B. You imply this identity, and that produces a 1. That's another identity. A and 1. That's an identity that produces a result of A. For this complex Boolean algebra expression, Boolean algebra just reduced the circuit to just plain A. And if you look at this truth table, when A is 1, the circuit outputs a 1. Certainly A all by itself is a far simpler circuit to implement than this Boolean algebra sum of products expression. Sum of products. Look for clues in the word sum and the word products. The term sum implies a single OR gate. Plus is the OR symbol. Sum is singular. Sum means one OR gate. Products with an S implies many AND gates. The star or asterisk is an AND. Products is plural. I must have multiple AND gates. Looking at the diagram, we have multiple ANDs feeding into a single OR. Sum is singular, so there's one OR gate. Products is plural, so there are multiple AND gates. Last and foremost, focus like a laser on the lines of the truth table that output 1. Sum of products has everything to do with these lines and nothing to do with the lines that end with 0. Sum of products, in short, says OR together all the terms that output a 1 in the truth table. The abbreviation SOP is often used for sum of products. Sum of products is a mouthful. Quite often we just say the SOP expression. Sum of products with 3 inputs on the truth table. Once again, we'll start with a truth table with 3 inputs, A, B, and C. Given these 3 inputs, I want to output F as the result of those inputs. Take the sum of products truth table, focusing on the lines that end with 1, and I produce a sum of products Boolean algebra expression. That Boolean algebra expression could represent a circuit that implements this truth table. The abbreviation SOP is often used for sum of products. First and foremost, focus like a laser on the lines of the truth table that output 1. Sum of products has everything to do with these lines and nothing to do with the lines that end in 0. Sum of products says look at the lines that output 1. These are all the lines of the truth table that output 1. When I'm doing sum of products, focus on those lines and those lines only. Boolean terms. Look closely at the first line with an S output of 1. Don't be fooled, I just renamed my output S here. Doesn't matter what letters we use for the input. Doesn't matter what letters we use for the output. Just watch them closely and make sure the terms reflect the letters. On this line, A is 0, B is 0, and C is 1. The Boolean term for that input read out loud is not A, and not B, and C. On a computer keyboard, you might type it this way or this way. Look closely at the second line with an S output of 1. A is 0, B is 1, C is 0. That produces a 1 on the output S. The Boolean term for that input read out loud is not A, and B, and not C. On a keyboard, it may be written this way or this way. Look closely at the third line with an S output of 1. A is 1, B is 0, C is 0. That produces a 1. The Boolean term for that input read out loud is A, and not B, and not C. On a computer keyboard, it may be this term or that term. Look closely at the fourth line of the truth table with an S output of 1. A is 1, B is 1, C is 1. The Boolean term for that input read out loud is A, and B, and C. On a computer keyboard, it might be typed this way. Sum of products, or the terms together. That's it. There's nothing hard about it. Below is the sum of products for this truth table with 4 ones. We have 4 3-input AND gates that feed into one 4-input OR gate. Here's my 4 AND gates, one for this here, one for there, one for there, one for there. I feed all 4 of these into an OR gate to produce the sum of products expression. First and foremost, focus like a laser on the lines of the truth table that output 1. Sum of products has everything to do with these lines and nothing to do with the lines that end in 0. Focus clearly here. We're going to do a second sum of products example with a different truth table. Let's build the sum of products expression, this truth table. Sum of products says look only at the lines that output 1. Boolean terms. Look closely at the first line of the truth table, F output of 1. A is 0, B is 1, C is 1. The Boolean term for that input read out loud, not A, and B, and C. On a computer keyboard, it might be typed this way. Look closely at the second line with F output of 1. A is 1, B is 0, C is 1. The Boolean term for that input read out loud, A, and not B, and C. On a computer keyboard, it may be here or this. Look closely at the third line with an F output of 1. A is 1, B is 1, C is 0. The Boolean term for that input read out loud, A and B and not C. On a computer keyboard, it may be typed like this or that. Look closely at the fourth line with an F output of 1. A is 1, B is 1, C is 1. That produces a 1 on the output. The Boolean term for that input read out loud, A and B and C. On a computer keyboard, you might type it like so. Sum of products or the terms. That is it. There's nothing hard about it. Below is the sum of products for this truth table with 4 ones in it. 4 3-input AND gates that feed into one 4-input OR gate. Here's the term for the first line of the table that produces a 1. Here's a term for the second line in the table that produces a 1. Here's a term for the third line and the fourth line that produces a 1 on the output. At this point, if you were good at Boolean algebra, you could use Boolean algebra to simplify this sum of products expression. Last and foremost, focus like a laser on the lines of the truth table that output 1. Sum of products has everything to do with these lines and nothing to do with the lines that end in 0. Sum of products says OR together all the terms that output a 1 in the truth table. The abbreviation SOP is often used for sum of products. Product of sums. Once again, we'll start with a truth table. Here is a truth table with 2 inputs, A and B, that produces an output F. From this truth table, we'll build a product of sums expression. Looks quite a bit different than sum of products. From this truth table, we'll build a product of sums expression. That product of sums expression can produce this circuit diagram. We're using all 3 parts of our circuit design trinity: the truth table, Boolean algebra expressions, and a circuit diagram. Product of sums. First and foremost, focus like a laser on the lines of the truth table that output 0. Product of sums has everything to do with these lines and nothing to do with the lines that end with 1. Product of sums says look only at the lines that output 0. Basically, if it's not this line and it's not that line, it must be a true. Eliminate all other factors, and the one which remains must be the truth. Sherlock Holmes. What we're doing is the opposite of sum of products. Look at this line. If it's this or that, it must be a 1. Product of sums goes the opposite way and says if it's not this and it's not that, the output must be 1. Boolean terms. Look closely at the first line with an output of 0. A is 0, we're going to change that to a 1. B is 1, we're going to change that to a 0. The Boolean term for that input read out loud is going to be A or not B. On a computer keyboard, you might type it this way. Now, why are we flipping the input? A is 0, and we change it to a 1 and make it just plain old A. B is 1, and we change it to 0 and make it not B. We want the term to be true when it's not A equals 0 and B equal 1. We're doing the opposite. We're saying if it's not this line, we want to output a 1. Boolean terms. Look closely at the second line with an output of 0. A is 1. We're going to flip that to 0. B is 0. We're going to change that to a 1. The Boolean term for that input read out loud is not A or B. On a computer keyboard, it may be printed like this. Why flip the input? A is 1 and we change it to 0 and make it not A. B is 0, we change it to 1 and make it plain old B. We want the term to be true when not A equal 1, B equals 0. When it's not this line of the truth table, we want to output a 1. Or the terms. Product is AND. The terms together to form the product of sums expression. Read out loud, this is A or not B and not A or B. If it's not the first line that outputs a 0 and it is not the second line that outputs a 0, it must output a 1. We're literally saying when it's not one of these two inputs, output a 1 for this circuit. Here's the circuit diagram. This circuit describes the product of some expression. This circuit implements the truth table above it. How would you prove that? For every possible input, A, B, does it have the exact same output, F? We can test each row. Row 0 right here, 2 zeros on the input produces a 1. When A is 0 and B is 0, then F is 1. Plug these values into the product of sums and it certainly produces a 1. A is 0, not B would be 1. I OR those together and AND it with not A is 1, B is 0. This produces a 1 for sure. That produces a 1 for sure. If I AND two 1's together, the result is a 1. Works for this row of the truth table. Plug these same values into the circuit diagram and it is also 1. Remember, not A is 1 when A is 0. Remember, not B is 1 when B is 0. A and not B is 0 and 1 fed into this OR gate, which produces a 1. Not A and B is 1 and 0 fed into this OR gate that produces a 1. Two 1's is an input to an AND gate, produces a 1. For row 0 of the table, both the product of sums and the circuit produce the proper output of 1. Testing row 1 of the table, when A is 0 and B is 1, F produces a 0. Plug these values into the product of sums, and certainly it does produce a 0. A is 0, not B is 0. You OR those together and you get a 0. Well, if 1/2 of the AND is a 0, then it has to produce a 0. Plug the same values into the circuit diagram and it also produces a 0. A and not B are both 0. Putting that into this OR gate, it produces a 0. Putting this 0 into the AND gate, it outputs a 0. Remember, not A is 1 when A is 0. Not B is 0 when B is 1. Test row 2 of the truth table. A is 1, B is 0, F is 0. Plug these values into the product of sums and it produces a 0. If not A is 0 and B is 0, this OR has to produce a 0. If 1/2 of the AND is a 0, it has to produce a 0. Plug these values into the circuit diagram and it also produces a 0. 1 on 1 on this input definitely produces a 1. But not A is 0 and B is 0, and that makes this OR gate 0, which makes this AND gate produce a 0. For this row of the truth table, both the product of sums and the circuit diagram output the same thing, 0. When A is 1 and B is 1, F outputs a 1. Plug these values into the product of sums and it certainly is a 1. 1 OR 0 produces a 1. 0 OR 1 produces a 1. Two 1's on the AND input and you get a 1 on the output. Plug those values into the circuit diagram and it also produces a 1. 1 OR 0 produces a 1. 0 OR 1 produces a 1. Two 1's on an AND input and you output a 1. We have proven the product of sum expression and the diagram correctly implement the truth table. All inputs produce the same outputs. What's the difference? Sum of products looks at the lines that end in a 1 here and here and says when the inputs match these lines, output a 1 for the sum of products or the circuit. Product of sums looks at these lines that end in a 0 and says when the inputs do not match these lines, output a 1. It's a little bit of reverse psychology, right? When it's not this, the circuit or the product of sums should output a 1. Eliminate all other factors, and the one which remains must be the truth. That's from Sherlock Holmes. Knowing when it's 0 is just as valuable as knowing when it outputs a 1. When it's not 0, the circuit must output a 1. Product of sums. The term product implies a single AND gate. Asterisk is an AND, product is singular. Product is singular, I need one AND gate. Sums implies many OR gates. The plus symbol is OR in Boolean algebra. The word sums is plural. It implies that I need multiple OR gates, and there are 2 OR gates. Looking at the diagram, multiple ORs feed into a single AND. For a product of sums expression, multiple ORs will feed into a single AND gate. Last and foremost, focus like a laser on the lines of the truth table that output 0. Product of sums has everything to do with these lines and nothing to do with the lines that end with 1. Product of sums says AND together all the terms that output a 0 in the truth table. The abbreviation POS is often used for producted sums as well as something else, but we won't talk about that. Product of sums with 3 inputs. Start with a truth table. P, Q, and R are the inputs to this truth table. It has an output of S. Look at the terms that end in 0 and produce a product of sums expression. From that product of sums expression, we can draw a circuit that represents this truth table. The abbreviation POS is often used for product of sums. Product of sums. First and foremost, focus like a laser on the lines of the truth table that output a 0. There's a 0 here, and a 0 here, and a 0 here, and a 0 here. Product of sums has everything to do with these lines and nothing to do with the lines that end with 1. Product of sums says look only at the lines that output a 0. Boolean terms. Look at the first line with an S output of 0. A is 0, we'll flip that to 1. B is 0, we'll flip that to 1. C is 0, we'll flip that to 1. The Boolean term for that input read out loud is A or B or C. Why negate the input bits? POS is looking for when the input is not 0, 0, 0. Boolean terms. Look at the second line with an S output of 0. A is 0, we'll flip that to 1. B is 1, we'll flip that to a 0. C is 1, we'll flip that to a 0. The Boolean term for that input read out loud, A or not B or not C. On a computer keyboard, it may be typed like this. Boolean terms. Look at the third line with an S output of 0. A is 1, we'll flip that to 0. B is 0, we'll flip that to 1. C is 1, we'll flip that to 0. The Boolean term for that input read out loud, not A or B or not C. On a computer keyboard, it may be this expression. Boolean terms. Look at the fourth line with an S output of 0. A is 1, we'll flip that to 0. B is 1, we'll flip that to 0. C is 0, flip it to 1. The Boolean term for that input read out loud, not A or not B or C. On a computer keyboard, it may be listed like so. Why do we flip the input bits? Because we're looking for when it's not this line. Product of sums and the ors. That is it, nothing hard about it. Below is the product of sums for this truth table with 4 zeros. 4 3-input OR gates that feed into one 4-input AND gate. This is the entire expression when you AND all of these terms together. And that's what product of sums does. It ANDs together the not of all the inputs that output 0. Remember Sherlock Holmes. If it's not this input, and it's not this input, and it's not this input, and it's not this input, it must be one of the other inputs. It must output a 1. Product of sums with 3 inputs. 3 inputs A, B, and C produce this output F. This is a different truth table, a truth table with only 2 zeros on it. First and foremost, focus like a laser on the lines of the truth table that output 0. Product of sums has everything to do with these lines and nothing to do with the lines that end with 1. Product of sums look only at the lines that output 0. We're trying to simplify circuits. Product of sums needs 2 OR gates and 1 AND gate to do this truth table. Sum of products would need 6 AND gates and 1 OR gate. Obviously, the product of sums would be much simpler for this truth table with 2 zeros than the sum of products. The product of sums on a truth table with 2 zeros would be much simpler than the sum of products on a truth table with 6 ones. Boolean terms. Look at the first line of the truth table with an F output of 0. A is 0, we'll change that to a 1. B is 0, change it to a 1. C is 1, change it to a 0. The Boolean term for that input read out loud, A or B or not C. On a keyboard, it may be this. Boolean terms. Look at the second line with an F output of 0. A is 1, flip it to 0. B is 1, flip it to 0. C is 1, flip it to 0. The Boolean term for that input read out loud, not A or not B or not C. On a computer keyboard, it may be typed like so. Product of sums. Product implies and. Sums implies ors. That is it. There's nothing hard about it. Below is the product of sums for this truth table with 2 zeros in it. 2 zeros in a truth table, it means I need 2 OR terms. 1, 2. 2 3-input OR gates that feed into one 2-input AND gate. Product of sums has an advantage here. There's only 2 lines that end with 0. It's going to produce a simpler expression than sum of products, which has to look at these 6 ones. What's the difference? Sum of products looks at the lines that end in 1 and says when the input match these lines, output a 1 for the circuit. So it has to look at all 6 of these ones. Product of sums looks at the lines that end in a 0 and says when the inputs do not match these lines, output a 1. So product of sums only has to look at these 2 lines that output a 0. It's really reverse psychology. If my inputs are not this line and not this line, then I must output a 1. Eliminate all other factors, and the one which remains must be the truth. Sherlock Holmes. If it's not this input and it's not that input, I must output a 1. Product of sums. The term product implies a single AND gate. The asterisk is AND. Product is singular. I need one AND gate. Sums implies many OR gates. The plus symbol in Boolean algebra is OR. Sums is plural. I need multiple OR gates. Look at this Boolean expression. Two OR gates feed into a single AND gate. Last and foremost, focus like a laser on the lines of the truth table that output 0. Product of sums says AND together all the terms that output a 0 in the truth table. When you look at this expression, we're ANDing together the two lines that produce a 0 in the truth table. Product of sums is often written without the star or the dot between the terms as it is above. Remember, AB is just A and B. This is these two terms ANDed together.
GameSci.com.